Okay, so doing more cubic splines. Yay. I guess this will be more helpful than my notes right now. Oh, that's right. I still have crummy chalk. Okay, I'm gonna get some good chalk. It's driving me nuts.
Oh, okay. I was about to say, oh, if you need a sweatshirt, I have one.
It's not freezing in here.
I can do this up. I'm cold, so you guys. Monday I'll go on a sweatshirt.
Okay. So, so our cubic spline has, all right, so we're on this interval with n plus 1 points to this. So with n plus 1 points, we have n pieces. So our pieces are defined by Si of x, y equals 1 to n. And they have this form with 4 coefficients, a's, b's, c's, d's. And we, instead of using power form, we use this shifted power form geared around the left endpoint of each piece. So this is a piece that's used for xi minus 1 to xi. So first piece is x0 to x1, second piece is x0 to xn, etc. So that's which piece is active on which subinterval. And so to recap from last time, the conditions on these pieces fit the data. So ai is equal to yi minus 1. So those are determined. And then we have the continuity condition. I didn't have such a good picture. So ai plus bi hi, where hi is the difference between consecutive x's. So it's the width of each subinterval. So h1, h2, h3, and so on up to hn. Those are the widths. Okay, so so a value at the right endpoint of each subinterval equals a value at the left endpoint of the next subinterval. And keep in mind, a n plus 1, that's not really a coefficient here, but we just define that to be the last y value. Just to have uniform formulas. Okay. And then continuity of the first derivative. And this is for I equals 1 to up to n minus 1. And then continuity of the second derivative, 2ci plus 6di hi is equal to 2ci plus 1. Dang it. Okay. also for I equals 1 to n minus 1. And that, as I mentioned last time, it determines almost everything. Because all these are the values of Si at xi, and this is Si plus 1 at xi, function, first derivative, second derivative. That was all covered last time. I've done nothing new yet. Okay, so there's a natural boundary conditions, which says the second derivative is 0 at the endpoints. So that says that C1 is equal to 0, and also the 2Cn plus 6 dn hn is equal to 0. Well, I'll make it uniform. So these are S double prime at x0 and xn, the endpoints. And then we also have the clamped boundary conditions, which state that, okay, so the first derivative, so b, b1 is equal to the given value f prime at the left endpoint, and then the first derivative at the other end, which would be bn plus 2cn hn plus 3dn hn squared, with f single prime at xn. So what we have are a total of 4n equations for each case, 4n unknowns, and then we try to figure out everything from there. And so where we got to last time, okay, the a's are known, so that's not an issue. But what about everything else? And where okay, a little fresh board for all this. Okay. Okay. All right, so we have formulas for the d's from the second derivative continuity equation, so ci plus 1 minus ci over 3hi, and that goes for I equals 2 up to, and I think I might have actually goofed before, because I only have that for I equals 1, 2 up to n minus 1. I think I'd written 1 to n before, because that comes from this equation, and we only have that for I equals 1, 2 to n minus 1. So that gives us not every single d, but most of them. But, so we get d1, d2 up to dn minus 1. What about dn? Is there something that I've written that tells us how to get d sub n?
Oh, you want us to solve for?
Yeah, where could what I've written?
3hn over cn, well, after.
Natural boundary conditions option.
Yeah, in fact,
Yeah, the second one.
either boundary condition.
Oh, okay.
Yeah, because this also has dn. So yeah, and actually, yeah, when I stayed after class and I was working these things out, that's one thing that struck me. I was like, what about dn? And I realized, oh, I should have just used that instead of that. Okay, so A's are settled, D's are settled, and then for the B's, okay, so we have. Alright, and this is put everything in one place, so AI is equal to y, I minus 1. Okay. And then the equation for the continuity, this one, we can use that to solve for the b's, because it's the only equation that has a b appearing in it only once. And I think that's pretty much where I left off last time. So we have bi equals, and I'm going to write this a little bit differently than last time. I'll write in terms of a's instead of, just to be consistent with my notes. So ai plus 1 minus ai over hi, because I mean we know what the a's are anyway, minus 2ci plus ci plus 1 all over 3 times hi. And this holds for, okay, I equals 1, 2, up to n, because we have a condition at all endpoints. Now the thing is, as far as indices go, like when we go up to Vn, we have a n plus 1, but we know what that is. That's yn, so that's not a problem. But then we have this unknown Cn plus 1, which is kind of strange. So what about that? Cn plus 1, we can define that by our, basically by our second derivative equation. That would basically be f double prime at xn over 2. Now, that's a convenient definition because that would be equal to 0 for natural boundary conditions, because that's what natural boundary conditions mean. That the second derivative at the far left and far right endpoints is 0. So in fact, what will happen is for natural boundary conditions, we just won't have this in here at all when I is equal to n. So that's not an issue. Now what about the case where we have clamped boundary conditions? So in that situation, here we have our second derivative at the the second derivative at the right endpoint of each subinterval from our second derivative condition. So it would be equal to, so I'm going to use that. So for a clamped case, I can define that to be Cn plus 6 dn hn. Okay. Not 6, 3. And this is from your second derivative conditions, because if I were to take my spline, my overall spline, that, take its second derivative and plug in xn, then this is exactly what I would get. If I take a second derivative, plug in xn, and divide by 2. So I can just define Cn plus 1 to be that. Okay, so now the other thing is, for clamped boundary conditions, I also have an expression for dn from my second clamped boundary condition. So that'll enable me eventually to that'll include Cn plus 1, and so I can relate all these things. Okay, so now I have a way to eliminate the B's, the D's, and the A's. The only thing left is the C's. And the only equation I haven't made use of yet is the equation that requiring the first derivative to be continuous. So I can take my formulas for my B's and D's and put them into that. It's the only equation that involves the C's only once. So, from a first derivative, that's no, this is for I equals 1 to up to n minus 1, where I have this. So, all right, so I have bi plus 2ci plus 3 di squared is equal to bi plus 1. So what I'm going to do is I have formulas for all of everything I need to plug in here, my B's and my D's, and never be over there. I'm just going to dump all that in here, and it's going to be a huge mess, and then we'll sort it out. Who knows, this may take the whole class, but honestly I don't care. Okay, so bi is ai plus 1 minus ai over hi minus 2ci plus, at least I know what I'm supposed to get because it's in my notes. Hi, so, okay, plus 2ci hi plus 3 di, so that would be ci plus 1 minus ci over 3hi hi squared is equal to bi plus 1. That's going to be this with the index shifted up by 1. So that's going to be ai plus 2 minus ai over hi plus 1 minus 2ci plus 1 plus ci plus 2 over 3 hi plus 1. Man, this is awful. So, and now keep in mind, I is going up to only n minus 1. So the largest indices we can possibly have in here are n plus 1. Now, an plus 1, we know what that is. Because so an plus 1 is equal to yn. And then ci plus 2, that could be up to cn plus 1. And we have definitions for that. So what's going to happen is, for natural boundary conditions, C1 and Cn plus 1 are both 0. So we really only have n minus 1 unknowns. C1, C2, C3, up to Cn. So n minus 1 equations. For clamped, we have n plus 1 unknowns. So I should be writing this down. Okay, so natural versus clamped. So for natural, we only have C2, C3, up to Cn. N minus 1 unknowns total. For clamped, we have C1, C2, Cn, Cn plus 1. So we have n plus 1 equations in that case. Okay. Now, okay, actually, if I take a look at this equation, for a case where I is equal to n, this is equivalent to this, and but I only have up to dn minus 1 in here. Okay. So the only place where Cn plus 1 appears is right here. But this gives me n minus 1 of my equations. So for natural boundary conditions, this gives me everything. It's the whole system. For clamped, I need all of these n minus 1 equations plus 2 more. The first of those equations, like it comes from the left side clamp boundary condition, like the equation for B1 basically. And then the other comes from the other clamped boundary condition involving like f prime of xn. So my two clamp boundary conditions will give me what I need. Okay, so here we can focus on only the interior equations. And this value needs to be simplified. So what I'm going to do is, I'm going to take everything involving c's and move it on one side, and everything involving a's and put that on the other side. So anything involving a's will go on the right side. So I'm going to have, also I'm going to multiply everything. Oh, okay, first of all, these threes will cancel. That h cancels with one of these. Okay, I don't have any other immediate cancellation, but now what I'm going to do is, I'm also going to multiply everything by 3, because I hate fractions. Okay, so on the right side I'll have 3 ai plus 2 minus ai plus 1 over hi plus 1 minus that, so I'm going to have 3 ai plus 1 minus ai over hi. Okay. What I found interesting is we have two of these minus ai plus 1 terms. This almost kind of looks like a second derivative approximation in a way, if we were to divide by h yet again. I don't know if there's anything significant to that, but it's kind of curious. Now, this, okay, then I'm going to have everything else. Okay, so I'm going to have, after multiplying by 3, and I have to remember not to do that. So I have 2ci plus 2, no, 2i plus 1 plus ci plus 2, hi plus 1, minus 2ci plus ci plus 1 hi plus 2ci hi,
6.
yes, plus 3 ci plus 1 minus ci hi. Now before I continue, did I forget to multiply by 3 anywhere else? No. Okay, good catch. Because that would have just sent me over the edge. Now, I need to, ultimately what I have over here is a matrix vector product. Matrix has entries depending on the h's, and the unknowns are a vector of c's. So I want to group this by c's, starting with the lowest index that I have. So the lowest index I have is ci. So for ci, I have minus 2 hi, minus 3 hi, plus 6 hi. So I put all that together and I have just 1 hi. So hi, ci, and then I look at ci plus 1. I have 2 hi plus 1, minus hi plus 3 hi. So I put all that together and I get 2 hi plus 2 hi plus 1, ci plus 1. And then finally, in front of ci plus 2, I only have hi plus 1. So equals all that stuff, which I don't need to change at all. Okay. So I have a system of linear equations with only 3 non-zero elements in each row for the interior points. So also for consecutive, like ci plus 1, ci plus 2. it's going to be a tridiagonal matrix. So, okay, so now I'm actually in a position to write out the system in full for the natural boundary case. For the clamp, there's still a little more work to do. All right, but we'll deal with the natural thing now. Well, actually, you're probably going to regret erasing that, but okay, well, you have notes. Okay. So, for the natural case, the solving system AC is equal to, I'll call it Y because it comes from Y values. So, A is a tridiagonal matrix. So down the diagonal we have, so 2H1 plus H2, these are the matrix, 2H2 plus H3, and so on, down to 2H n minus 1 plus Hn. Because this would be an n minus 1 by n minus 1 system. And then on the subdiagonal, we have H's. So we have H2, H3 down to Hn minus 1. And then on the super diagonal, we also have H's. So like in the first row, we're going to have H2, H3 down to Hn. Your C vector is C2, C3 down to Cn. Now, those equations over there, they do involve C1 and Cn plus 1, but we already know those are 0 due to boundary conditions. And then finally, your right-hand side, so we have 3A3 minus A2 over H2 minus 3A2 minus A1 over H1. So these differences of A's, which are Y values, which is why I called the vector Y. And then down to the last one, right, 3AN plus 1, which is also YN, over HN minus 3AN minus AN minus 1, all over HN minus 1. Okay, so that is the whole system to get all your coefficients for natural boundary conditions. And then once you have that, I've written on the other board how to get the D's. And okay, so we have AI is yi minus 1. We have BI, which is minus AI over HI minus 2CI plus CI plus 1 over 3HI. That works for I equals 1 to n, where if we encounter C1 or Cn plus 1, we'll just say it's 0. And then Di is C minus 1 minus Ci over 3HI minus 1. And then for the boundary condition, we have for the second derivative, well, in fact, Yeah, since we need the second derivative to be 0, and that involves dn. So in fact, this applies all the way up to n. Where and the part where it's n is from s double prime at xn being required to be 0, and we would fill in 0 here for Cn plus 1 to make that happen. Okay, so there you have it. You solve a system of equations, get the remainder of your coefficients from these conditions, and you have your spline. Woohoo. Now, what's interesting about this system of equations is this matrix, not only is it nice as tridiagonal, it is strictly diagonally dominant. In fact, if I want to be extra rigorous, I should say row diagonally dominant. What that means is in each row, so the diagonal entry is greater in absolute value, strictly greater than the sum of the absolute values of all other elements in that row. And what we get out of that is guaranteed, no matter what the h's are, and the h's are definitely positive, but A is invertible. And if you want to see why having a simple condition satisfied guarantees that's invertible, take 610. So,
Cracks me up how you promote your own class, right?
Yeah.
It's like you're selling us these products.
Yeah. Yeah, you're pretty shameless. I should wear a tacky tie or something. Now, although Haley, who's already taken that class, I guess you're the only one in this room who has.
Oh yeah.
Yeah. I don't recall if I explicitly covered that thing, but oh well.
Yeah, I think you did.
Okay. Yeah, because it's actually pretty easy to prove using like a Gershgorn circle theorem for eigenvalues. So. Okay, so that is a natural boundary condition.
Yeah.
What?
That just sounded like gibberish, but you know.
Yeah, and to think.
This, and that.
Yeah, and to think in a semester it won't be. You can gibberish everybody else. Okay, so now that half the class is gone, let's take a look at clamped. Well, much of the work for clamped has already been done. So in the clamped case, so natural, and this is what emphasizes the n-1 by n-1 system. So the clamped case, we have, again, a c is equal to y, except a is now n plus 1 by n plus 1, because the endpoint unknowns c1 and cn plus 1 are not necessarily 0 anymore. So equations 2 through n will be exactly the same as these. But then we have to use the boundary conditions for everything else. So we have B1 must be equal to, I'll call this Z naught, which is the value given for f prime at x naught. But we have a formula for the B's. So if I fill that in here, that means I must have A2 minus A1 over H1 minus 2C1 plus C2 over 3H1 has to be equal to Z naught. So what will end up happening in that case, if I just rearrange this, I have, okay, so I'm going to multiply 3 by 3 to get an equation that's kind of like these. So I'm going to have 2H1C1 plus h1 c2 is equal to a2 minus a1 over h1 times 3 minus 3 z naught. And please look at the degree of what I have in my notes. Yes. And the thing is, it kind of makes sense. It's kind of like this first equation, because what do we have here? A difference of y values over an h. What is that? That's a derivative. And that's what we have here. So, okay, and I'll fit this into a matrix in just a little bit, and you'll see that it actually conforms to the pattern. Now, the other thing we need is, for the other, so for, that's one boundary condition. For the other boundary condition, we need bn plus 2cn hn plus 3dn hn squared. That's the derivative of the last piece at the right endpoint. Has to be equal to zn, which is f prime at xn. So now, if I were to fill in all of those things, then what do we get? So we have bn is going to be an plus 1 minus an over hn minus 2cn plus cn plus 1 over 3 hn plus 2cn hn plus 3 dn, which comes from the second derivative, form of second derivative, so we get, okay, so dn is cn plus 1 minus cn over hn, 3hn, times hn squared is equal to zn. And then we could do some canceling here, but 3's cancel. This cancels with one of these. And of course, they're going to multiply everything by 3 again. So, okay, so what's going to happen in, okay, I have to make sure to get this in the right order. Okay, so I want to keep this where it is. So if I rearrange this, on the right side I'm going to have 3zn minus 3 an plus 1 minus an over hn. And it's kind of like if you took this last row and bumped all the indices up by 1, this would become this, and this would be like a derivative at the endpoint times 3, which is what we have here.
Wait, can you repeat that? I'm sorry.
If I take everything here and shift the indices by 1,
Okay.
but here what I have, an plus 2 minus an plus 1 over hn plus 1, it's kind of like a derivative
Oh, okay.
times
Okay.
3, and that's what I have.
Cool.
Okay. And then everything else that's left, oh, wait, okay, I have b, okay. So I have stuff multiplied by 3, so I have minus 2 cn plus 1 hn plus 6 cn hn plus 3 cn plus 1 minus cn hn equals all that. Okay, so then if I combine all these terms, I have hn cn, and then for cn plus 1 I have plus 2hn cn plus 1 equals all this. So I'll just emphasize in this mess what my two boundary equations are. So these equations, along with the other equations I already had for the natural case, make my n plus 1 by n plus 1 system. So now I can go ahead and write that out in full, and you'll see that it isn't, in overall appearance, it isn't really all that much different. Just having 2 extra rows. Okay. So. Okay. So I can solve for the C's. And then I would just do all this to get the A's, B's, and D's. That part is not going to be any different. The boundary conditions will have already been taken into account just to make the system. Okay. Now, so we have A is really going to have the exact same structure, just starting one sooner. So we have,
Oh, you moved your thing.
what?
Your thing. You didn't move it?
Ah, that would have been awful to find out later.
Thank you.
Okay. All right, so we have, so in the first row, we're just going to have 2H1. And then in the second column, we're going to have H1. And then zeros everywhere else. And then the other equation starts, so we have, okay, well, whatever I have in the first row there. So I have H2, okay, so one difference is, like in the natural case, in this equation, that I didn't have anything because this is a column for C1. That element would be 0. But here I actually do have something, H1, and that was there all along. It's just that in the natural case, it was multiplied by an unknown that we knew was 0. So then we just,
Wait, how is it an unknown that you know?
well, unknown until you take the boundary conditions into account.
Okay,
That
okay,
immediately gave away its value.
okay.
Okay, but yeah, that, I guess I asked to be jumped on for that.
Sorry.
Okay, and then we get down to the last equation from interior points. And I was going to need a bigger matrix. So I have, okay, so on the diagonal, I have 2hn minus 1 plus hn minus 1. And then over here I have an hn, which in a natural case would have been multiplying. Hold on, I might have messed up on the previous board. Oh, okay. On the previous board, that should be an n minus 1. Okay.
Which one?
This entry. I had hn, it's supposed to be hn minus 1. Okay. Okay. And then the last row comes from the equation at the very bottom that I've boxed. So I have in the subdiagonal entry, I have hn. And in the last diagonal entry, I just have 2hn. So the pattern kind of continues. It's just that, like, if the way this is going, I have h1 plus h2, h2 plus h3. Back here, I only have h1 because I'm not going to have an h0. Here, I'm only going to have an hn because I'm not going to have an hn plus 1 because I don't have those subintervals. So that's my whole matrix. It's again tridiagonal, and it's also strictly row diagonally dominant, so the same invertibility property applies. And then my right-hand side, so, well, yeah, I have everything written down there, so, and now you can see the pattern better. So that's my, for my first boundary condition, and then for my last boundary condition, and then these same right-hand side elements in between. Okay, so there. Now I'm going to use up probably most of the class time. Yep. That's the n plus 1 by n plus 1 system to solve for clamped boundary conditions. So yeah, we have, you know, at the beginning 4n equations, 4n unknowns. You could just solve those, but if you can get to a system like this that has a nice structure to it, and then work out everything else in very simple formulas after that, why not? So,
Excuse me.
yeah.
Why we use row there? Why not column?
Oh, sorry, what?
Why we use strictly row diagonal? Why we don't use column? What makes this?
Well, and so it happens to be column diagonally dominant also. Now, the way we prove invertibility from this involves, since it deals with eigenvalues and eigenvectors, like matrix vector multiplication. So that theorem is proved using the rows. So, so yeah, we could say, oh yeah, it's also column diagonally dominant. That knowledge just doesn't get us anything. Of course, if a matrix is invertible, then so is its transpose. So. Okay. Now, I'm going to fall behind again. I mean, I have an example that's done in the notes where you just set up the system and go ahead and solve that. So it's really not that interesting, more tedious than anything else. But basically, it's for natural boundary conditions. So you're setting up as if you have 5 points, so you have 4 subintervals. You really just have a 3x3 system that I've written out, and then you're getting the A's, B's, and D's from there. Using these formulas. So, at the risk of not falling further behind, I wouldn't dream of doing this in undergrad class, but hey, you're tough grad students, you can handle it. And just look at that example, because the thing is, that's not really how things work in MATLAB anyway. And the command in MATLAB to do splines is just called spline. And you give it a vector of x's and a vector of y's, and it returns a structure that has all the information about the spline, like what the coefficients are and all that. And MATLAB has convenience functions if you want to evaluate the spline at any point. And if you just pass in the vector of x's and the same number of y's, it does natural boundary conditions for you. But if you pad your y vector to have an extra value at the beginning and an extra value at the end, it assumes clamped boundary conditions and assumes that those extra values are the derivatives, the z naught and zn. So what it does is it basically sets up this system of equations, does this little backslash thing, and then computes the remainder of the coefficients from there. Okay. Now, I'm going to, well, be a foolhardy teacher once again, and I have an interesting property to prove about cubic splines that's similar to a property from a property for linear splines. Because linear splines, we saw that the first derivative of a linear spline is like the flattest. It has a smaller 2 norm than any other function in the right function space that interpolates f at the knots. So with the spline, the cubic spline has the least average curvature possible. So what I mean by that specifically is so really I have S double prime 2 norm is less than or equal to 2 norm of V double prime, where V is any function in the Sobolev space H2 of AB. Now, with linear splines, I talked about H1, so that's where the function is, where a function itself is absolutely continuous. So here, it's where a first derivative is absolutely continuous. And I think, actually, Stephanie, borrow your textbook for a second. Might be, since I don't have my notes in front of me, I might be messing stuff up. I'll make sure. Okay.
Do you want your notes?
That's
Yeah, I
this
have
one.
them right here.
Okay. Well, it's the exact same thing here.
Oh, cool. Never mind then.
Okay. So H2 is oh, okay. Yeah. Okay. So actually, I did get that right. So a quick rundown of H2 means that V prime is absolutely continuous, and V double prime is in space L2 of your interval AB, where L2 is the space of all functions that are square integrable. And so V has to be this function space, and V interpolates F at all the knots. So among any functions that fit F and have these satisfy these continuity conditions on their derivatives, this has the smallest average curvature. Now, what's interesting is the second derivative here is not required to be continuous. It could be like piecewise continuous. Here, the second derivative is required to be continuous, because that's part of the equations that we set up here. Okay. Now, the proof of this is actually in the textbook, but I'm going to take a shot at it, even though I don't have it in my notes. And I have a brief comment about how it can be done, and then it's similar to what I did last time for linear spline, although I probably have to use the textbook's more difficult approach. Because I mean, for linear spline, I was able to do a simpler proof than what the textbook has. Probably not so lucky this time. Okay, and if it aborts, I'll probably just run out of time. And then I'll be forever behind, but there's so much time left at the end of a semester that I don't really care. Okay. So, attempted proof. So if I take a similar approach, that would mean that I'd be looking at 2 norm with S double prime, which would be equal to S double prime minus V double prime plus V double prime. But I'll work with norm squared. Okay, so then I can look at that squared plus norm of S squared plus twice the inner product of S double prime times V double prime with V double prime. And this is exactly what I did in the linear case, because the idea is if I can show, in the linear case I showed that this was 0. And that gave it away because that meant that this would be equal to okay, so no, I think I had it backwards. I did. I need to switch my V and my S. Because I wasn't looking forward to looking at this in a product. Yeah, okay, so if I show that this is 0, or even if I show that it is at least non-negative, then I get from here to here only by adding non-negative or positive things. Therefore, it must be less than or equal to. So what I need is, so this must be greater than or equal to 0. Now, I actually have no idea if I'm supposed to prove it equals 0, like in the linear case, or just that it's positive, but we'll find out. Okay, so what I can try is if I look at the inner product, which would just be the integral from A to B of V double prime minus S double prime times S double prime, and perform an exercise in integration by parts. And the only question is, which way is this exercise supposed to go? Okay, so if I were to do, I have to keep my boundary conditions. Okay. Yes. This requires natural boundary conditions. And that's what makes me think I can pull off this proof after all. So I'm going to let this, integration by parts, I'm going to let this be my u. And I'm going to let this be my dv. So that means my integration by parts is going to be u times v, which will just be v prime minus s prime, with limits a and b. Natural boundary conditions. What do they tell us about what's happening at the endpoints?
0.
What is 0?
X. The endpoints are
What?
First,
0. The
third,
endpoints are 0.
No.
At the second derivative.
Second derivative is 0 at the endpoints. You have a clamp imposes a condition on the first derivative. So I'm plugging the endpoints into this, and I know it's 0. So gone. Yeah, so I'm hoping that the rest of this will continue to be as destructive. So now I have minus integral of v, which is v prime minus s prime, du, which is s triple prime. Okay, now this is a cubic spline. The third derivative is going to be, it's not continuous, it's going to be piecewise constant. Okay, so what I could do is write this as a sum And now I have SI triple prime, which is just a constant, times integral of V prime minus S prime. Okay. So what can I do now that makes this a whole lot easier? That I couldn't really do just having it written in this form and not knowing what S triple prime is. What can I do about integral?
Write it like quadrature.
No, easier. What? Yeah, what I get?
Oh,
Zero.
B minus B array minus S.
Yeah, because I'm integrating a derivative. Cancels out. So this is,
Oh, right.
oh, okay, this is on each endpoint, xi minus 1 to xi. I forgot that. But the point is, this is v minus s with limits xi minus 1 and xi. But how do v and s relate to one another at these points? Well, they're not zero individually. But what condition are we supposed to satisfy about what their values are at the nuts? It's on the other board.
Oh, they're equal to each other, right?
Yeah, because they're both equal to f. Whatever function you're trying to fit, s and v, yeah,
So since when you
That.
subtract them, you get 0.
right there. The spline fits this by definition. Yes. So yeah, these differences will all be 0. So, yes, this whole thing is 0. So therefore, S double prime, its norm is equal to what would be double prime squared minus, and since this is equal to norm of V double prime squared minus something that's positive, so I can just replace that with that.
Oh, that's not one rule, right?
What?
Is that a rule, like what you're doing with the norms?
Oh, this or that?
That.
No, that's just algebra.
Okay. No, I'm just.
Now that this is gone, I just rearranged.
It just looks familiar, and never mind. I know what I'm talking about, but I can't say it. Okay.
Oh, like a reverse triangle inequality kind of thing?
Yeah, that's one thing.
It's not exactly that.
Okay.
Okay, so wow, I was able to do that proof. I really couldn't believe that. I mean, this is everything I tell. Well, yeah, 2 of you Math 500, learning to teach, and they're like, oh, I'll just go off script and see what happens. But I wouldn't. I generally would not do that in an undergrad class. Okay. Any time left at all? Hardly any. And that's not a bad thing. Okay, I have a read QX spline. I'm over it, let's just stop. And it's a natural stopping point, so there you go.
It is so cold.